Welcome to another podcast. This episode we're going to be taking a look at properties of integrals. We're going to start with what is probably the most important set of properties, and that is that the integral behaves like a sum because, remember, it kind of is a sum. So if you look at the integral from a to b of f of x plus or minus g of x. So if you try to take the derivative of a sum of two functions, that is equal to the integral of the first plus or minus the integral of the second. Okay? The second property I want to take a look at. If we try to take the integral of a constant c times a function, then I can factor out the constant just like we would with the sum. If you had a constant that was a part of every term in a sum, you could factor it out. And it's the same thing here. So this is the constant times the integral of the function. And these two properties together, so these two properties together are what are called linearity. So this is basically saying that the integral has the linearity property, and so here c is a constant. So we think of the integral as being what we call a linear operator. In other words, it's an operation that obeys the distributive law. I can distribute the integral, and it obeys scalar multiplication laws, which means I can factor out scalars or constants. All right. The third rule here is that if I look at the integral from a to b, and interpreting this in terms of area is going to help, and I add to that the integral from, let's say, b to c of f of x dx, then pictorially what I'm doing here is essentially this. I'm taking the integral over an interval from a to c, and so I've got some function here. The first integral is going from a to b, and so the way that I sort of interpret this is the first integral is adding up the area here, so that's the first integral. The second integral is adding up the area here, and there should be no reason why the area under the curve from a to c, so this is the function f of x, there shouldn't be any reason why the integral or the area from a to c isn't the same as taking a to b and adding it to b to c. And that's what the property says, that the integral from a to c, just going straight a to c, is going to be equal to splitting it up, a to b, b to c. All right. The fourth property is sort of piggybacking off of the previous property, and that is if you take the integral from a to a of f of x dx, this should be 0. Well, why? If you think of your rectangles, the rectangle's width is always going to be 0 if you have no width to your interval. So you've got to have an interval to actually put rectangles on to define the integral. And if you can't put a rectangle on the interval and the interval has width 0, then the integral is 0. There's no area under a curve. So if I have an interval of width 0, right, there's my interval. It's got a height, but it's got no width, so the area underneath the curve there is 0. All right, property number 5. Integral from a to b of f of x, so this is the area under the curve from a to b, is equal to the negative of the integral if I try to reverse the limits. So these are called the limits of integration, and if I go from a to b, that's not the same as going from b to a, because I get negative the area. Now, this is best explained with the previous example where we were interpreting the fundamental theorem of calculus in terms of velocities and positions. This is like saying I start at point A and I go to point B. This is saying I start at point B and go back to point A. So if one direction was the forward direction, then the other direction would be considered the backward or negative direction. And so if I interpret my function as velocities, it makes a lot of sense that this would be negative. I got positive velocity in one direction, negative in another direction. So just remember, anytime you switch the limits of integration, you will produce a negative sign, because it's in one direction I'm adding up distances, in the other areas I'm subtracting out or taking away distances. Notice that this is consistent with the fundamental theorem of calculus, because if I was to evaluate this, this would be the negative of, if I take the antiderivative of this and call it f of x, it would be f at a minus f of b, and that's the negative of f of b minus f of a, and that's exactly what we would get on that side. So this is consistent with the fundamental theorem of calculus to make this a negative and reverse it. Finally, the last property here is if f of x is less than or equal to g of x, then the integral of f of x is less than or equal to the integral of g of x. And that should make a lot of sense. If the heights are all lower for the function f of x, the heights of the rectangles are lower, then there's less area under the curve f of x than there is g of x. And that's all that that's saying. So these are our basic properties of integrals. You'll talk about some more of these properties in Calculus 2 as you dive further into how to calculate integrals for special cases. But these are sort of the main properties that help us understand the integral and calculate the integral for various functions. All right, thank you for watching.